This demonstration looks at a model of the initial phase of a liquid quenching process called film boiling, which happens when a vapor layer separates a hot solid from a cool liquid. Quenching into liquid media is an extremely complex process involving a variety of physics operating on vastly different scales. The near-wall boiling processes that strongly influence heat transfer from the part to the quenching medium operate on a scale that is many orders of magnitude smaller than the component size. One of the more interesting things about this model is how we use COMSOL's custom PDE interface capability to accommodate these different scales. In the graphics window, we see a cutaway view of the model. The outer cylinder represents an oil quenching bath, and the inner cylinder, or puck, is a piece of solid metal that is placed into this bath at a very high temperature and rapidly cooled. A surface plot of the volume fraction of vapor is shown in the oil bath domain, while a surface plot of the temperature is shown on the puck. White is the hottest, black on the edges is the coldest. Let's animate these results in time. This video shows about 40 seconds of the cooling process, during which gas bubbles are quickly formed along the walls of the puck and then float up and out of the top surface. During the 40 seconds, the temperature in the outer areas of the puck drops from over 1050 degrees C to under 950 degrees C, while the interior of the puck is still relatively hot. This multiphysics analysis solves for multiple variables, including the temperature field histories of the puck and liquid, as well as fluid flow variables for a two-phase turbulent bubbly flow. And as I just mentioned, the film boiling layer is modeled using a custom proprietary set of boundary equations. By clicking on this custom general form boundary PDE interface, we can see the boundaries where these equations are defined. The thickness of the film layer is not explicitly represented by the geometry, but rather by this custom set of boundary equations. The boiling layer thickness, which of course in reality has some finite value, will not be explicitly modeled. Instead, the boundary PDEs approximate the mass, momentum, and energy transfer in the boiling layer. COMSOL's custom PDE interfaces, available with the base package, easily allow for these equations to be coupled with the conjugate heat transfer physics. Let's take a few minutes and go through an overview of how this model was set up. First, the geometry. Over here on the left, we have the model builder tree, and we have this node here called Geometry 1. This is where the geometry is built. And as you can see in the graphics window, the geometry is pretty simple. It's a 2D axisymmetric geometry of the puck in the middle of the cylindrical bath of quenching liquid. The red vertical dotted line is the axisymmetry axis around which the gray domains are revolved. Taking advantage of the axisymmetry of a problem is a big memory and time saver. Now, it's worth pointing out that, as you just saw, we were still able to visualize the results in 3D. This is a really nice feature in COMSOL, where you're able to take advantage of symmetry when solving, while at the same time you're not limited to having to view the limited space dimension when it comes to viewing your results. So that's the geometry. As far as the materials definitions, that's accomplished under this materials node here. The puck is made of a nickel-based superalloy called Inconel 718, and the COMSOL material library contains this material with temperature-dependent heat transfer properties, as you can see here. The liquid is a generic quenching oil. The equations to be solved are specified under 4 physics interface nodes shown here in the model builder tree. 1, 2, 3, 4. First, we model heat transfer in the puck and in the liquid with 2 separate heat transfer interfaces. This is an easy way to allow the temperature at the boundary between these connected domains to be discontinuous. Remember, we aren't explicitly modeling a domain for the boiling layer Rather, we are solving a set of PDEs directly on the boundary. Heat flux boundary conditions out from the puck and into the liquid are used to couple the two sets of heat transfer equations at the interface. Let's talk about the heat transfer equations and boundary conditions for the puck. The default axial symmetry condition is accepted along the symmetry axis. Under heat flux 1, a general heat flux is applied using a variable called heat flux puck. A negative sign is added because heat is flowing out of the puck and into the liquid. This particular variable, heat flux puck, is defined in the model builder tree under definitions, variables 1. The exact expression is grayed out due to its proprietary nature, but I would like to say that this variable is a function of solution variables described and solved for by the custom boiling layer PDE interface. These variables can be seen under the dependent variables section of the general form boundary PDE boil layer interface here. If you expand dependent variables, you can see two variables that we're solving for, BL1 and BL2. And if this expression weren't grayed out, you would see that this heat flux puck variable is a function of those two solution variables. So this is how the equations are coupled. Very easy to do in COMSOL. In addition to that heat flux boundary condition, there's also a surface to ambient radiation condition applied to the surface of the puck, and that's going to contribute along with that heat flux that I just described. So this will fully define all the conditions needed to arrive at a meaningful solution to the temperature field in the puck. A similar setup is used for the heat transfer in the fluid, and we won't cover the details in this demonstration. The turbulent bubbly flow interface here is used to model a two-phase flow consisting of the quenching liquid and the vapor that is produced due to evaporation near the hot component. A gravity domain condition is applied to the fluid to allow for buoyancy effects. G const is the predefined variable for the gravitational constant. The wall-to boundary condition applied to the top of the fluid domain allows for the liquid phase to flow tangential to the boundary, but not normal to it, while at the same time allowing the gas to flow freely out of the domain. Another nice feature in COMSOL is that if you ever have any doubt about what boundary conditions you're applying, you can always view the mathematical equations in the settings window here, under this equation section. Whenever the Navier-Stokes fluid flow equations are solved, it is required for uniqueness that the pressure be specified somewhere in the domain. That's why we have this pressure point constraint condition. As you can see, we've specified a pressure of 0 pascals at the upper right corner of the domain. Probably the most interesting boundary condition for this interface is the wall 3 condition here. This is applied to the boundary where the liquid touches the puck. Notice a gas mass flux condition is applied by this variable, gas flux. Similar to the custom heat fluxes applied earlier, this variable is also defined under definitions, variables 1. And it's also a function of the boiling layers variable solved for by the custom interface here. So that's a brief overview of the physics setup. Let's move on to meshing. Under Mesh 1, we see a custom meshing sequence is set up that includes a boundary layer mesh in the fluid domain at the boundaries where the fluid touches the solid. Right here. This is an efficient way of solving the strong gradients in the solution variables in this area. Now that I've shown the setup for our geometry, physics, and mesh, the next step is to solve. Solving is done in COMSOL using the study nodes, and as you can see, the time-dependent form of the equations is solved. In this case, we're solving for a period of 40 seconds running from a time instance of 43 to 83. All variables are solved for simultaneously using a segregated solution approach. I already have the solution stored, so I won't resolve. But in order to compute the solution, right-click on the study node and select Compute if that's what you wanted to do. The time-dependent solver completes in about 30 minutes on my machine, which is an average current market workstation. We already saw an animation of the vapor forming and the puck cooling down in time at the beginning of this demo, but I did want to show some of the other solution variables that we could look at. This is a 2D plot of the volume fraction of the vapor, and as you can see right here along the outer edge of the puck is where a lot of the vapor is coming. Notice that right away, this is at a time instance of 45 seconds, which is 2 seconds into the cooling process. Notice that right away the boiling layer begins releasing the gaseous phase of the oil into the surrounding liquid, with the highest concentrations being along this outside vertical surface of the puck. And then the bubbles quickly flow up and out of the fluid. And that's due to the buoyancy effect that we included. And then here under this thickness of film results plot, I have a visualization of the film thickness layer. And this is the 2D axisymmetry axis goes right along here. And what I've done is mirrored that 2D data across this axis here. So what we're visualizing here in gray is the full diameter of the puck, and in blue is the full diameter of the quenching liquid. And this tube plot with the height expression defined gives a visualization of the thickness of that film boiling layer. Areas in dark red correspond to a thickness of about 6 millimeters, and areas in dark blue correspond to a thickness of less than 1 millimeter. As expected, at the bottom of the puck, the vapor is trapped underneath due to the upward buoyancy force. The spikes here, here, and here, those correspond to areas where relatively large amounts of gaseous bubbles are being introduced into the liquid. Again, here's the plot that we showed initially of the puck cooling in the oil after a time of 40 seconds. And as you can see, the areas on the outside have cooled relative to the inside of the puck. This completes this demonstration.